Okay, so next part of chapter 3, we can't talk about scientific measurements without units. Remember, every measurement is a number and a unit. So we're going to get into talking about the units that we use here in chemistry and in all of science, really. Make sure that you've got your calculator with you and your paper and your pencil and everything so that you're taking notes and you can kind of follow along with what we're doing. So the units that we use in science are part of a system called the SI system. Okay? SI is French for Système International de Units. Right? It was developed originally in France, but really France was just the place where all of the different countries met. So for hundreds and hundreds of years, most countries around the world had their own system of measurements that they used. All right, so England had their own, Germany had their own, Japan had their own, China had theirs. Everybody had their own system. And it was fine if you never left your country, right? If you only dealt with the people that were around you in your country and you all used the same units, then it didn't matter. What the problem was is eventually we got to the point where people started traveling around the world. You know, once the explorers started realizing that you could sail the oceans and get to all sorts of different places, and then we started coming up with even better ways of getting around the world, like trains and planes and all these different things. Eventually, you get to the point where if somebody from France is going to meet somebody in Russia, and they want to deal with each other in terms of how much of something they have, they're going to need a common system of units, and this started becoming a problem. So it wasn't but maybe, a little over 100 years ago, 150 years ago or something like that, that all the countries finally decided, you know what, this is crazy. Going to each country and dealing with their own set of units. We need to have one system that everybody around the entire world uses. And we're going to make sure that it makes sense and it never needs to be changed, ever, right? So this is where the SI system originally came from. So France invited every country from all over the world to come and sit down and make up a new system together that everybody then would agree to follow. And it was great. Everybody came, they came up with this system, and they all went back to their countries, and we have this new system of units that we all need to start using. And most people in most countries said, oh, that sounds like a lot of work. We have to change everything from the units we were using before now to these new units, and it's going to cost a lot of money, and But most countries just went ahead and eventually did it. It may have taken them 10 or 20 or 30 or 40 years to kind of get everything changed over, but they eventually did it. Well, not all countries. Even though the United States was there at that meeting, even though the United States did agree to change over to this new system of units for their everyday measurements, we never did. There's lots of reasons. All right, the biggest one that's usually cited is it costs a lot of money. And yeah, it would cost a lot of money to change everything over to a new system of units. But I do want to go through and talk about why this system of units is better than what we currently use. And let's talk about what we currently use now in the United States, right? So in the United States right now, we use something called imperial units. It has been since kind of updated to be called the U.S. customary units, since the U.S. is about the only country that uses these units anymore. But the original system was called the imperial system because it came from our original country that we all came from. Well, not all, but the country ourselves came from, which was England, right? Originally, the U.S. was an English colony. And back in the 1700s, when England was in control of America, England's system of units was called the imperial system. And they used things like feet and yards and miles and pounds and ounces and Fahrenheit those were all the units that they used back then. So, of course, we adopted those here because a lot of people here were following what they did in England. Now, since then, England has changed over, as well as most of the world has changed over the SI system. But we continue to use this system, this imperial system of units. Now, let's talk about how dumb the imperial system is. All right, follow along with me. So, how many inches are in a foot? You all know this, right? There's 12 inches in a foot. So, why 12? Why did they choose 12? I don't know. Why didn't they pick 10 or some easy number? They picked 12. How many feet in a yard? There's 3 feet in a yard. Why 3? Why not 5 or 10 or some easy number? How many feet are in a mile? You know that one? Most people don't. It's 5,280 feet in a mile. Huh? Why that number? That's a really hard number to remember and use. How many ounces in a pound? 16. 16? Why 16? None of this makes any sense. What's the freezing point of water in Fahrenheit? Oh, I know. It's the random number 32. What's the boiling point of water in Fahrenheit? Most people don't know this one off the top of their heads. It's 212. Huh? You remember all that? Now, you may remember some of those simply because you've been in school learning about them for many, many years, so it seems kind of natural to you. But it is not a smart system. It doesn't make a whole lot of sense. So why we're still using it doesn't make a whole lot of sense. And in science, we want to make sense. So guess what? We use the SI system. Now, the SI system is based on the metric system. So it's based on the powers of 10. So everything in it, every single thing that we do in the SI system is based around the number 10. Not 16, not 32, not 5,280, not any of these other crazy numbers. Everything's based on 10, or powers of 10. So 10, 100, 1,000, million, whatever. All powers of 10. Everybody can count by tens. Therefore, it's a really easy system for anybody to use. And the only reason why you would have any trouble with it is just simply because you probably haven't been working with it much in your life. You spent so much time in that other system that this one seems foreign to you, even though it's better and makes more sense. Now, here's one reason why it is a better system. All of the units for the basic measurements that we have to make are all based on physical events that occur in the natural world. You know what the foot was originally based on? Yeah, it was somebody's foot originally. So that poses a problem if we're basing things on things that can change, like somebody's foot. These units are not based on anything like that that would change. For instance, length we use the meter as the base unit for length. A meter is the distance that light travels in a certain amount of time. Now, that's never going to change because the speed of light doesn't change. It doesn't matter where you are. Anywhere. You could be on a different planet and it would still work. You wouldn't have to use some guy's foot. That's why it makes so much more sense. Time is in seconds. Now you're like, well, it was in seconds already in the old system that we still use. You're right, but what we base the second on is different. In the current system, in the imperial system, a second is a portion of an astronomical day. Now, what does that mean? Well, you know that our day is based on how much time does it take for our planet to turn or rotate around once, right? That's what a day is based on. And our year is based on how long does it take our planet to go around the sun. You know what? Those things aren't even numbers. We make them even. Like, how many days does it take to go around the sun? How long is a year? You know that? Most people will say it wrong. No, it's not 365 days. It's 365 and almost a quarter days. Huh? Well, we can't have a quarter of a day. So what do? We just save up those quarter days that were off each year, and then we put one full day on every 4 years. What do we call that day? Leap day. That's right. We just had one earlier this year. So we're good for another 4 years. But a full day isn't even 24 hours. We call it 24 hours, but it's not. It's like 23 hours and 56 minutes. So it doesn't make any sense that our seconds are based on things that actually are not even, they're not even themselves. So a second now in the SI system is based on the cesium atom. The cesium atom is an atom that is radioactive, and it spits out particles on a regular basis. Never changes. It's always regular. Okay, so that second is actually based on a phenomenon that never changes. And this is why sometimes you'll even see that really accurate clocks in this world are called atomic clocks, because they are based on cesium atoms. And all the rest of these that are on here, all of these are based on these kinds of natural phenomena that never change. You need to know these 7 base units. Length is the meter. Mass, the base unit for mass is the kilogram. That's the tricky one. It's not a gram, it's actually a kilogram, because a gram's so small. The time, the base unit is seconds. Electric current is measured in amps. Temperature is measured in kelvins, although we're going to talk about Celsius is fine. Amount of substance is measured in something called the mole, which second semester in here we're going to talk a lot about. And luminous intensity, right, how much light there is measured in candelas, which we're not going to talk much about. But you need to know what those base units are. Now, here's the next great thing about the SI system. There are 7 base units. Guess what? That's the only units you need to measure every single thing in the entire universe. Everything in the universe could be measured using those 7 base units. Well, that's pretty easy. So all we have is 7 units, and all of the units follow the metric system, which is based on powers of 10. Who wouldn't want to use that system? Oh, wait. Wah, wah. Those are all the countries in green that are using the metric system. Countries in red don't. So the US, Liberia, and Burma are the 3 countries that don't use the SI system. Come on, US, get together. Make it better. Anyways, we're going to continue on learning the SI system because it's important for us to use. So let's talk about that metric system. So the metric system, you're probably familiar with already, right? Things like kilo and hecto and deca and deci and centi and milli and those prefixes. I like to use something I call the King Henry method, and maybe you've seen this before. A way to remember the prefixes in the metric system is to remember a silly phrase like, King Henry died by drinking chocolate milk. No, the sentence itself doesn't make any sense, but the letters in front of each of those words help you remember the prefixes in order. K is for kilo, H is for hecto, D is for deca, B is for base, D is for deci, C is for centi, and M is for milli. So those are the prefixes, but it's hard to remember kilo, hecto, deca, base, deci, centi, milli. It's easier to remember King Henry died by drinking chocolate milk. Now, if you don't like that phrase and you have something else you want to use, go for it. Doesn't matter. Okay? All right. So, in each of these prefixes, we have a power of 10 that it stands for. So, a base unit is based on 1, okay, or 10 to the 0 power. Deca is 10 times bigger than that. So, it would be 10 of the base unit, or 10 to the 1st power. Hecto then would be 10 to the 2nd power, or tens times 10, which is 100. So hecto is 100 times bigger than base. Kilo is 1,000 times bigger because it's 10 to the third power. Or we could go smaller. Deci is 10 to the negative first. Centi would be 10 to the negative second, or 100th. Milli is 10 to the negative third, which is 1,000th. And since we're only moving by powers of 10, then if you want to convert one of these prefixes into another prefix in the metric system, all you have to do is move your decimal point around. So to convert one prefix to another, just move your decimal point. Want to go from base to deca? Then move the decimal point one place to the left. Or you can move it 2 places if you want to go to hecto, or 3 places if you want to go to kilo. If you want to go to the right, then you're going to use those smaller prefixes. So it's just moving the decimal point around. And to tell you the truth, there are more than just these prefixes that we need to know. In fact, you remember on that useless number, that's funny, useful numbers, I know you're all getting a chuckle out of that. They are actually useful. In the useful numbers page that I posted, the useful numbers page, I have all of the prefixes that I want you to know. Remember, I said you need to know everything from tera all the way down to pico. So where do the rest of them fit in to this? So let's add them to this. And I'm going to add them on to this. I don't have it printed, but I'll have to draw them in. So if you go 3 decimal places bigger than kilo, you actually get to something called mega. So if it's 3 places past kilo, and kilo is 10 to the third, then mega must be 10 to the 6th, right? If you go 3 decimal places past mega, you get to giga. So that would be 10 to the 9th, otherwise known as a billion. And if you go 3 decimal places past giga, you get to tera, which is 10 to the 12th. That's a trillion. So a terameter would be 1 trillion meters. A megameter would be 1 million meters. We could also go smaller than milli. If you go 3 decimal places smaller than milli, you get to micro. Now, the symbol for micro looks like a U with a tail that comes off the front, that hangs off. Okay, so that's the Greek symbol mu, but it stands for micro. We can't use M because M's already being used for milli. If we go 3 places smaller than micro, we get to nano. So nano would be 10 to the negative 9th, or 1 billionth. And then we get to 3 places smaller than nano, which would be pico, which would be 10 to the negative 12th. All right? Okay, so what we should be able to do is go between any of these prefixes, all the way from tera all the way over to pico and back. We should be able to go through any of these places just by moving decimal points. So let's try some examples. All right, first example. I want to change 10 grams into milligrams, right? 10 grams into milligrams. So gram is the base, right? There's no prefix in front of it. It's just gram, so it must sit here at the base. And I want to go to milli. So if I want to go from base to milli, I have to go 1, 2, 3 places to the right. So I'm going to take my decimal point, which would be right here. I'm going to go 1, 2, 3 places to the right. So what number does that become? 10,000. So there are 10,000 milligrams in 10 grams. All right, let's try another one. 1.62 meters into centimeters. So again, this is just meters. So meters is the base. So I want to go to centimeters. So centi's right here. So that would be 1, 2 places to the right. So I'm going to take my decimal point, I'm going to move it 1, 2 places to the right, and that becomes the number 162. So 1.62 meters is 162 centimeters. Seeing how this goes? Let's try another one. 5,229 kilometers into hectometers. So this time I'm not starting at base, because this time I'm starting at kilo, K. So I'm going to start at kilo, and I want to go to H, hecto. I'm going to go from kilo to hecto. So that's one place to the right, right? If I start at kilo, go to hecto, that goes to the right, one place. So I'm going to take my decimal point, and I'm going to move it to the right one place. So now that's 5,200, or 52,290, right? Because we have that 0 at the end now. How are we doing? Does this make sense? Hopefully it does. You're going to have to try some of these on your own. So I'm going to put up the rest of these, and I want you to try the rest of these on your own. You can pause it, and then I'll come back and I'll show you what the answers are supposed to be. All right, so here are the rest. Go ahead and pause it, try these out on your paper, and then come back. Okay, so hopefully you did do that. You tried these out. Hopefully they make sense. Let's go through them real quick. So this one is 0.00844 milliseconds, and I want to go to just regular seconds. So I'm going to start at M, milli, and I'm going to go to base. So that means I'm going to go 1, 2, 3 places to the left. 3 places to the left. So 1, 2, 3 places to the left means that I now have more zeros here. So this is going to be 0, 0, 0, and then the original zeros, and then 844. Because I already had these 2 zeros. I'm moving past this one, and then I'm adding 2 more before I get to the decimal point. So that was a total of 5 zeros. So I have 5 zeros, 844. The next one, dk. dk is deca. Sometimes they'll also write it as dA for deca, but most of the time it's written as dk. They can't just write d, because then it would get confusing with deci. So deci is just d. dk is deca. What does capital A stand for? Well, that's amps. So this is deca amps to milliamps. I want to go from deca to milli. Well, deca to milli, so that's 1, 2, 3, 4 places to the right. So I'm moving 1, 2, 3, 4 places to the right. So that's 5, 1, and then 3 more zeros. All right, I'm going to throw the rest of the answers up here, just so you can see them. And then real quickly, I'll just explain them. I'm not going to go through and do every minute of them. Let's just go through and do them quickly. MOL is the abbreviation for moles. So this is base unit of moles. This right here is millimoles. So base to milli is what I'm doing here. So 1, 2, 3 to the right. So 1, 2, 3 to the right. That's how I got that answer. The next one is kilograms to centigrams. So kilo to centi. Kilo is here, so I go 1, 2, 3, 4, 5 places to the right. So I had to take this and go 5 places. That's why I added in 5 zeros. By the way, some of you may be looking at these really big numbers or really small numbers and going, shouldn't we be writing those in scientific notation? Yes, you are correct. But for now, I just want to get the whole moving the decimal point thing down before we move on to scientific notation rules again. The next one, this is just a D, not a DK, so this is deci, so this is decimeters to kilometers. So I'm going deci to kilo. Deci to kilo is 1, 2, 3, 4 places to the left. So I went 4 places to the left with this. So you notice how you're going to be working with this. As long as you remember these in order, then you're just moving your decimal point back and forth. This is seconds to milliseconds, so that's base to milli. And the last one is just amps to deciamps. So it's just base to deci, so they just had to move it one place. All right? So that's basically it. Like I said, there's more than just the units the prefixes that we talked about. So this is really all of them that exist out there, but you only need to know from tera to pico. We don't really go any further than that. Right, so that's what you need to memorize to be able to do. And you can see here in the middle is, again, the base. This is their base area here. And they throw in some other ones that we'll eventually talk about. Right, but everything that would be a base unit would go right here in the middle. All right, so that's the beginning of units. And on the next lecture, then we'll talk about the derived units, how we can put units together to come up with other units, like watts and joules and meters and liters and things like that. And then we'll also talk about the temperature scales. So I have to mention Celsius and Kelvin to you guys.